Welcome. This is the first example of calculating flexural stresses, and we'll use actually a very fun exercise with that. So we will analyze the flexural stresses developing in a skateboard. And what's the better than checking flexural than a skateboard? So we have here an assumption of a person of weighing 180 pounds. They lean more forward, so more of their weight, or the weight here, goes to the front foot of 100 pounds. So you need to draw a Freebody diagram and providing it here with the dimensions. And also you need to do statics, and I already done that because the problem here is not a statics problem, it is a strength of materials problem. But you have to do, depending on the problem, you will have to do, of course, statics to figure out reactions and also the internal forces. So this is what we are initially after, is we trying to figure out where is the maximum stress in this skateboard. And to find the maximum flexural stress, which is a normal stress from bending moment, I need to find the maximum bending moment in that skateboard. So what I will do is I will start drawing shear and moment diagrams. So I hope you remember these from your statics class. So the top one is the shear in pound, and the lower one is moment in pound-inch. And I will start drawing the shear. The cantilever ends of the skateboard, like the really front and back parts of it, I don't have really any action happening there, so I will ignore that part up to the reaction RA to the left, and the other part, the opposite side, the edge of the skateboard, up to the reaction RB. So starting from the left, we start drawing shear and moment diagrams from the left. I start from 0 and I hit RA, so I will jump by 102.7 pounds. I will go straight, no distributed load, so I will hit now 100 pound the load of the front foot, getting me down to 2.7 pounds. Go straight, no distributed load, hit the 80 pound, that will bring me to 77.3. And then I will hit RB, which will bring me to equilibrium of 0 at the right roller here. To draw the moment, if you remember, we calculate the area under the shear diagrams. So I calculate also these, A1, A2, and A3. And starting from the left, similar thing, the left tip and the right tip of the skateboard, there are no loads there, so I'll start from the roller, the left one. And the roller is allowing rotation, so the start was 0. And then starting with 0, adding A1, because A1 represents the delta of the moment between a point of the roller and the reaction RA to point of the load 100 pound. So 0 plus 410, that will be 410.8 internal moment at the 100 pound point. And then moving from the 100 pound point to the 80 pound point, I will add A2. And A2 here will bring me up to now the moment value of 464.8. And one thing I would like to correct here is that the A3 value is negative value. So this one here is negative 77.3, which will result in A3 to be negative 463.8 plus the value that I ended up in the moment, 464.8. That will bring me almost close to 0. It will be a 1 pound-inch. Considering that my moment values are up to 400 pound-inch, that 1 pound-inch will be a rounding error accepted. It's less than 1%. So from here I can have a conclusion that the maximum moment in this skateboard will be 463.8, 464 actually, 464 pound inch. So I will correct that also. 464. So with this moment, I will be able to calculate the maximum flexural stresses. So I have moment Mmax, and I will need to calculate now the inertia, moment of inertia matching that bending moment, and also pick the C value that represent the point where the maximum flexural stress will happen. So by looking at this cross section of the skateboard, I see here that I that will resist the maximum moment will be the I around the z-axis, and it's the width of the section that's parallel to the z-axis is 9, but the dimension that's really resisting the moment here is to the power 3, which is the the thickness here, which is ½ inch. So I end up with this value in inch to the power 4. And when I plug in the values into sigma max, it's the moment I have, the inertia I have, and then C, which is half of the depth of the skateboard, which is 0.25 inches, and I will end up with a maximum flexural stress of this value. The thing is, just correcting here this value to be 464.8. So the same value should be still applying for sigma. So we have the maximum normal stress from the bending, sigma max. And one thing to note here, that also kind of to get a sense of what's this value relative to the failure point. So sigma ultimate here will of plywood, which most of the skateboards are made of, is 2000 psi. So if considering the factor of safety, that sigma max might be actually a very critical point and might cause failure here to the skateboard. So in future lesson, we'll talk about composite sections. We'll see how we would strengthen this skateboard with a stronger material to avoid the failure and breaking the skateboard here under the load we have. All right, so this was example 1, a fun example to consider, skateboard example. And this next example, we'll see a case of flexural stresses in a beam. Thank you and take care.